In this section we continue the discussion of periodic motion. Here we have a video of a balanced wheel as a demonstration of a simple harmonic motion. A balanced wheel is used for automatic devices that are not battery operated. Old clocks use this type of mechanism to make analog clocks work. These types of devices would require a periodic winding to promote motion. Shown here are the concepts behind a balanced wheel, which is a mechanical machine. The moment of inertia of the balanced wheel is about its axis. A coil spring inside the wheel exerts a torque that is proportional to the angular displacement from equilibrium position, which is written as k times theta, and it is negative. K here is a constant which is called a torsion constant. This restoring formulation is equal to its moment of inertia times the angular acceleration. We take the derivative form of this formula and rearrange it, and we get an expression of the double derivative of theta shown in equation 10.25. Therefore the motion is angular simple harmonic motion. So, like linear motion equations of motion which have a rotational equivalent, we also have an equivalence of the linear simple harmonic motion, which is the angular simple harmonic motion. The equations for the equivalence of linear acceleration, angular frequency, period, and frequency are shown on the right side. Here we have a simple pendulum which is oscillating back and forth from an origin. Looking closer to a simple pendulum, which is an idealized model consisting of a point mass suspended by a massless, unstretched string. The restoring force on the bob is proportional to sine theta, but for a very small displacement sine theta is approximately equal to theta. The restoring force for a simple pendulum type of motion is given as the negative of mass times gravitational acceleration times sine theta, shown in equation 10.29. Note that for a pendulum the restoring force is not proportional to theta but to the sine theta, so the motion is not simple harmonic. But if we take the assumption earlier that sine theta is approximated to theta, which suggests that the angle is very small, then it behaves like a simple harmonic. Then the restoring force can be expressed with this approximation as negative of mass times g times x divided by length L, as shown in equation 10.30. We can equate both sides of the equation and we see that the spring constant k is equal to mass times gravitational acceleration over length L for a pendulum behaving in a simple harmonic motion. Now we go deeper. We substitute this k to the angular frequency equation and we get that the angular equation can be expressed as shown in equation 10.31. We can also write an equation for a pendulum type of system for frequency and period shown in equation 10.32 and 10.33. Here we have an example of a physical pendulum. It is still a pendulum, but the body has an irregular shape. A physical pendulum consists of a rigid body that rotates around a pivot point. Gravitational force acts on the body at its center of gravity, cg. The restoring torque on the bob is proportional to sine theta. The restoring torque is produced by the weight. Again, for a very small displacement sine theta is approximated to be theta. This approximation of motion is simple harmonic motion. Again we have the same condition or assumption set in order that the system is operating as a simple harmonic type of system by the condition that sine theta is approximately theta. This is for very small changes in theta. Now since we are dealing with a rigid body having multiple masses as its composition, we take the sum of torques of its individual components. We see that the restoring torque is equal to its moment of inertia times the angular acceleration. Rearranging this equation we get an expression for the angular acceleration for a rigid body assumed to be operating in a simple harmonic motion. You can compare this to a linear equation for simple harmonic motion for acceleration. Here we have comparisons of the linear acceleration and we get an expression for the angular velocity, frequency, and period for the angular type of system shown in equations 10.38, 10.39 and 10.40, respectively. Here we have an example. Suppose we have a uniform rod oscillating. Find the period of the rod. Here we recall that the moment of inertia of a rod is 1/3 times the mass times the length squared. Here we recall the equation for the period with a factor containing moment of inertia. Substituting the moment of inertia of a rod with its axis at the center, we get that its period is about 1.64 seconds as it oscillates. Here we have a summary of different equations for simple harmonic motion. We have the linear system, angular system, simple pendulum system, and the physical pendulum. It is important to analyze the problem of what type of system before applying any of the equations. Here we have a wave on a string simulation from PhET simulation. Here we can see the effects of the quantity called damping. The string under a low damping and we see that it behaves like a regular wave with its amplitude very similar in terms of height. However, when large damping quantity the wave behavior changes and this is noticeable by the decrease in its amplitude. We see this in nature and objects that there is a force that reduces the oscillation to an eventual resting position to its equilibrium. So, damping is like the friction for simple harmonic motion. This simulation is free and you can access them easily at phet.colorado.edu. Here we have an example of damped oscillation where a mass is attached to a spring and allowed to vibrate. As shown here, when little damping is introduced the system will oscillate with similar length of amplitude. However, when a considerable amount of damping force is introduced the system slows down with decreasing amplitude till it goes back to its equilibrium position. The decrease in amplitude caused by dissipative forces is called damping, and the corresponding motion is called damped oscillation. Frictional damping force denoted by F equals negative BV where B is a constant that describes the strength of the damping force. We see that the net force is the sum of the negative K times X minus B times V. The equation has the negative Kx which shows the spring behavior of the string. Summing the forces along the x-axis we get that negative k times x minus b of the damping force times velocity equals to Newton's law mass times acceleration. Expanding this to its derivative form we get that it appears to be a second-order differential equation with a solution shown in equation 10.43. The solution for the function 10.42 is an exponential function which is typical for systems that have sine function appearance. We also have the angular velocity of these type of system that have damping shown in equation 10.44. When the angular velocity is 0, the body reaches an equilibrium, and we get that the constant is equal to 2 times the square root of the spring constant times the mass shown in equation 10.45. When this occurs, we call this critical damping. Here we have a table for different events for the constant b. As mentioned earlier, when b is equal to 2 times square root of k times m, the system no longer oscillates and returns to equilibrium or critical damping. When b is greater than, there is no oscillation but returns to equilibrium more slowly than critical damping. This is called overdamping. When b is less than, the system oscillates and steadily decreases amplitude. This is called underdamping. That is it for now, and I hope you learned something new today. For questions and comments you may send them to diyslearningstuff@gmail.com. You may review the slide on YouTube at @diyslearningstuff. Note, please do not forget to use your school email. Also write your complete name and class section. Thank you for listening and see you next module.